But you are just referring to that page. Can you go back actually to that page, exactly that page? I'm on the agenda page right now, on the Indigo page. Where is this link on that?
You see at the bottom, the fun4all simulation details.
Yes.
And there's, the whatever, some little write-up, and at the bottom you find HTTPS
I see it
www
now.
Phoenix EIC tutorial.
Okay, great. Thank you so much. I see it.
We actually should see it on your chat on your screen now. So.
Yep. Thank you so much.
So this is where you get it. Right. Okay, let's see how this goes. It's always a little delayed. So this is the first tutorial of the session here. It's simulation based on fun4all. And just to get this out of the way, when we wrote this thing, I had a son who was like 5 years old, and he always went there. And we thought, okay, that's actually a pretty nice name for something which actually enables you to have quite a lot of fun. So this is where the name comes from. We have our own logo. This thing has closed in the meantime, but the software is still running. So the structure here, what I'm going to do is a short introduction into fun4all. Then I call it example 0. So I take Jaroslav's Luminosity Monitor and try to run it within fun4all with the least possible modifications. Then I'm going to go into fun4all for real. So there's this simple example detector, how to put it into fun4all, how to run it, what you can do with it. Then the second example, especially for people developing, silicon detectors or TPCs, how you can do a quick momentum resolution estimate, with a configurable silicon detector. I left out the TPC, sorry. And then the third example, take your detector, so I take Jaroslav's detector and put them into a full detector implementation. And list of other things you can do with it. Not sure if I have that one. And then, where you can get help and like the future, how this is going to go. So what I assume is that you have a basic C++ knowledge, that you kind of know what a base class is and virtual methods. Some basic familiarity with root, that you know what a root macro is, and that you can draw histograms and n-tuples. As of now, we support root 5 and root 6, but root 5 is being kind of phased out. So if you look into macros and everything, you will find sections for root 5 and root 6. Again, if you want to do yourself a favor, just go for root 6. Don't try to backpropagate to root 5. You can run the software now either with your RCF account that works out of the box, or on your desktop. There are instructions how to do that. That was sent around yesterday. You should have some familiarity with Git, so like what is a repository and how do you clone things. And what you definitely want for the future when you work with that is a GitHub account. So a brief history. So the development started in 2002, so it's mature, and has been used by the Phoenix collaboration, which was a heavy ion experiment here at RIC from 2003 on reconstruction and analysis of basically starting in 2003, going until Phoenix shut down in 2016. At that time, we were running, and basically many subsystems had developed their own way of doing things independently, and that had to be basically put under one umbrella that you can actually run the show together. And they always compare programming as like herding cats. Everybody who ever had a cat knows that this just doesn't work. The only thing you can do, you can feed them, have a door that they can go out, they come back, and you clean their litter box. And that's basically the approach we take. Is we don't tell people what to do. So it's basically a toolkit. You feed them, means you give them input data, and they go out, do their stuff, and they come back and drop something in your litter box, and you basically feed it to the next getter. Yes. and then you clean it up afterwards. And the only problem is when they start fighting outside, then you actually have to do something. Otherwise, they can do whatever they want, as long as it's basically the results are correct. So the development was clearly driven by reconstruction analysis needs, not by beauty or abstract design considerations, rules. That went out the window fairly quickly for the subsystems. Its modularity is a key. As I said, it's a toolkit. You have single components. You can add some, you can modify them, you can remove them without actually having to go full blown into the code and change everything everywhere. Plenty of functionality was added over the years. Some of them is always surprising, like, oh, look, we can actually do that. I forgot. So there's, some of stuff is actually waiting to be rediscovered. In 2011, we started adding Geant 4 as a subsystem. So from then on, we can run Geant 4-based simulations. And in 2015, we split off from Phoenix, and followed by cleanup and lots of modernization. And down there, you find a link to the framework code itself. So what does it do for us? It reads input files, many different types. It writes output files, again, many different types. You can, automatic saving of your selected data objects. So your code doesn't really have to, take care of the saving. It basically just dumps it on the node tree. And as I said, we clean the litter box and make sure it goes into the right place. It somewhat manages the node tree. That's the litter box and the feeding station, where things get data from input data back. So that's our storage for data objects. More on this later. You call the reconstruction analysis modules in the order in which they were registered with fun4all. So the correct ordering is the responsibility of the user. fun4all will not complain if you reconstruct the tracks before you reconstruct the hits. So you just won't get any tracks, and you have to figure out what went wrong with it. But the assumption is that the user kind of knows best, and you don't want to start overriding the user and then having to override the override to get the user to do what they want. So we can make snapshots at any stage of the reconstruction analysis. So the node tree can be basically put into a file right back, and you can pick up where you left off. And you have access to calibrations. So fun4all has been our workhorse now for 16 years. We ran raw data reconstruction analysis, simulation, embedding, and it's petabyte-sized data sets with billions of events. So it's very well debugged. So coming to the structure of the system, let me put on my glasses so I can actually see. So the main guy is here, the fun4all server, which sits on top. That's the thing you communicate with. So you get a pointer to this. There's an instance. And via this one, you communicate with the rest of it. You have input managers. They can read, we call them DSTs, these all-term data summary tape, right? So these are basically root files. It can read our raw data format. So we have test beam data. We can read test beam data into it. We can read the usual HepMC. There's an old standard called Oscar. I'm not sure if it's still in use, but never mind. We can read it. Then EIC smear. And you want to have an empty thing if you just want to drive the event loop. For particle generators, you basically just want to kick off the event loop. Then, as I said, you've got the node tree. Again, comes later. Our data structure. And then you have analysis reconstruction modules, which then get called by the server in the order in which they were registered. The reconstruction modules themselves, they can read calibration. So we have an interface into a Postgres database, or they can read them back from a file. Due to the quirkiness of root, you actually have to take care of the histograms and n-tuples you're writing, because it has this old idea that you open a file and it puts a local directory there. You create the histogram there. You close the file, your histogram's gone. So that needs a bit of coding. So there's a histogram manager which makes sure that the histograms stay with you and that you can save them into a root file. Again, you can also save trees and n-tuples in the meantime. And then we have an output manager. So that thing can write DSTs. If you read raw data in, it can basically strip the raw data. So it can write our raw data format, and it can also write HepMC format. Again, if the input file is in HepMC. I don't know why you would do this, but it's possible. So, yeah?
Can I ask a question?
Sure.
On your previous slide at the bottom, you say make this format no vector communication.
Oh, One thing you learn very quickly is people love singletons, where you basically have some object which contains data and they start fighting with each other. So the idea is that these guys, they don't talk to each other at all. So then you can actually keep them nice and, like the cats, if they don't interact with each other, it's good. So the simulations, they are Geon 4 based, so we don't have access to Geon 3 or Virtual Monte Carlo. It's fully integrated into our analysis chain, so we basically treat it as just another analysis module. The Geon 4 installation itself is modular design, so again, all detectors are self-contained. Again, the idea is that one detector cannot interfere with the other detector. You don't want that. The whole show is configured with root macros. We have a bunch of generic detectors, boxes, cylinders, cones. So it's basically you can implement them right in the macro. You say, I want a cylinder of that size, with that diameter, that length, and I want it at that position with that rotation. And it will basically put it there. We have from our EIC activities, we have a full suite of EIC-specific sub-detectors. So we've got RIDGE, we've got a forward calorimeter, HCal. So there's a whole bunch in the forward hemispheres. It's in the meantime, it's 8 years of development. So this thing we've been, through quite a lot of development cycles and debugging and making things better, work better. We have 2 published EIC detector concepts based on this, where the simulation provided the vital input, and we have some tutorials for newcomers you might want to look at. So now coming to the program flow within fun4all. So this, so we've got the server sitting here. This is the node tree where the data goes in and out. On the right side, you have the Geon 4 universe, again, nicely separated. You don't want to interfere with each other. So the first thing you have is an event generator. That means it can be an input file, it can be a single particle. We have Pythia 6, Pythia 8, Sartre, so we have some inbuilt event generators. And what they do, they basically populate what Jaroslav mentioned, this particle table for Geon, and basically put this put this on the particle stack in Geon 4. The main module, which does the communication, which the interface to Geon 4 is this PHG4 Reco. This deals with the detectors. So it initializes Geon 4 before all the detectors are added. So it needs some choreography. A lot of times you have to, for example, when you want to change the physics list, Geon 4 has to be instantiated to read the physics list before Geon 4 starts the messenger that you could change it. So basically these things in a Geon 4 only implementation, you actually have the hard code. And here we basically cache these things that we can change it on the macro before we actually kick off Geon 4. So that's part of this one. Detectors itself, they're implemented. There's naturally an interface routine between this one and to G4 Reco. And the only thing which is necessary for a detector is you have to provide a construct method, just like in Geon 4. It is actually the Geon 4 construct method. And then what you need is a stepping action. So what the stepping action does, you basically from Geon 4, as Jaroslav mentioned, for every step this thing gets called, you have to figure out if it's actually your detector, and if so, you have to do certain things. And this is the place where we extract the hits from Geon 4 and put them back on the node tree. The detectors are modular, so you've got 1 detector, 2, I think in the meantime it's like 20 or something chained up. So each detector is its own entity, providing the flexibility for complex setups. Then if you had that step, so the stepping action, they put the Geon 4 hits onto the node tree, and then you can run the regular reconstruction chain. So what then comes typically is digitization. We have an entry for the raw data, so if you test beam data, they basically go at that point onto the node tree, and then you run tracking, clustering, and jet finding, epsilons, photons, you name it. And at every point in time, you can write the whole thing into the output. That also makes sure that you have a common reconstruction for the raw data and simulated data. So you certainly don't want to have 2 different frameworks for raw data reconstruction and simulation.
Okay, sorry.
Yeah.
Can you enter the raw data input with the Monte Carlo data?
Yeah, for the
Again, construction.
nothing talks to each other. And actually, I mean, I point the raw data over here. Basically, the raw data is just another input manager up here. So they are fed in by an input manager. So now the input, the event generators we have currently. So I took the easy way out. I said, okay, EIC SMER has all these nice EIC EP EA event generators implemented. So hey, you know what? I'm just going to read their output. So this is basically how I deal with these things. And then fun4all has, in addition, a few other event generators. So Hygiene, that's a heavy ion event generator. We have, Pythia 6, Pythia 8 we can run inside, Sato we can run inside. Jetscape needs a bit of work, but in principle can be read as well. Generic HepMC2, so HepMC3 is still too much in flux that we can actually really use that, which is the holdup for Jetscape. We have a bunch of single particle generators, and we can actually do embedding of events. So, putting raw data and simulated data into the same chain is possible, and we can keep track of these things. That's pointed out down here. So what you need when you want to track the input particles, basically see what they do to your detector, you need to preserve the truth information. So you have to basically be able to say, okay, I found this thing in the reconstructed output. Where did it come from? Does it actually have an origin, or which input particle actually generated those? So we have the full truth information. Anything can be traced back to the input particle. Here are just some event displays. So this is a very peripheral heavy ion collision, just to show you both what we're up to. So this is our EIC detector implementation. That's a Sato event, and it looks only that messy because something hits the, it's two particles coming out, but something hits the hadronic calorimeter and makes a big splash over here. So this is what you see over here. NASA Space Radiation Lab, they're interested in shooting, heavy ions into water to see what it does to the astronauts. So they are using this a bit, and down here is basically just one of our mock-ups where you have Pythia 8, 6-layer silicons, detector mock-up, and a 2 Tesla magnetic field. So these are all things you can basically do on the macro level. So distribution, as you can imagine, if I would tell you, oh, you have to build all this yourself, you would be busy for quite a long time. So there's quite a few of third-party software involved. So what we decided to do, so we have the operating system image, that's the SL7 distribution, which is run here in RCF. That comes in form of a singularity container. They're working on a Docker image that should come up in a couple of days. Libraries and third-party packages are installed in CVMFS. So you basically just pull them out of CVMFS, which is available worldwide, which means, the packages are centrally maintained. So you don't have to worry how to, use CMake for this package because you have, it doesn't really work correctly. We have a dedicated EIC CMFS volume as of day before yesterday. So there is something you can all get to. The open science scripts are readable without any keys. You need 2 shell scripts to actually set up the environment. So this is the EIC setup script, which basically sets up the environment variables that you can run everything. If you decide to build your own code, local code, then you have to run this little script over there, which with your install area, which then sets up the root include path, adds your directives to the root include path, to the LD library path, and to the path. And the only reason why you need a shell script over here is that the root include path is kind of funky.
Is there any difference between these and the standard SVNX?
No, except for the name. See, I said EIC setup. If you look at it, it's a soft link to SVNX setup. Okay. But in case we have, I think at some point they will have to separate in there. So we should get used to this one. Okay, now how to build your own package. So what we do, we use the AutoComp AutoMake, the auto tools to build our code. So we're not trying CMake. I think it's too complicated. And I have to yet see a CMake installation which actually works in all cases. So it's very complicated and extremely hard to debug if it doesn't work. Disadvantage, the nice thing with CMake is you have a build area and leaves everything there. You screw up, you want to redo things, you just wipe out the build area and it doesn't touch the sources. Sadly, this one does put some files into your source area. So if you just commit everything to Git, then all of a sudden you end up with some auto-generated files in there, which get overwritten when you rerun it again, but just for hygiene. No? Each package, brackets directory, is built by itself. So we don't build basically the whole show with one big makefile. We have it compartmentalized. Again, it makes it easier. You basically look at the directory, at the package you're working with. You can compile it locally and add it with the setup local to your installation. So just in terms of hygiene, how you should deal with that, you should really keep your source built and install areas separately, but you should use a common install area. You can basically dump everything into the source area, but it's a mess, and you will be very unhappy if you do that. So you have a source directory, then you make a build directory. You call a little shell script autogen with a full path to the source directory, minus prefix, the install directory, and there should only be one because you're set up locally. You don't want to have a too long LD library path and root include path. Then you run make install, and basically the libraries end up in here. If you have another package, you basically make another directory, you put in another directory, make another build directory, call this again, and goes in the same install area. In the examples, you always see that I'm basically doing a /autogen. If you want to use the debugger, you have to give it the full path, so otherwise the debugger can't find your source file. Yeah. So now let's get to Jaroslav's Luminosity Monitor. So the project is, as he pointed out, is your 4-based simulation and uses handmade root trees to save the output. So the goal, initially, I looked at that code, it's like, oh yeah, let me change everything. It's like, that's probably not a good idea. So let me just see what I can do with the minimum changes. And that's something I started on Wednesday. And I was actually putting my own horn. I was surprised how easy that was. I didn't expect it to be so easy. So the approach is basically using the fun4all, detector scheme what I have basically as a wrapper around Jaroslav's code. So that's, the wrapper certainly needed adapting. There were quite a lot of changes compared to all the other subsystems, but Jaroslav's code didn't really have to change. So the changes were needed were, since now fun4all takes over, you have to remove the detector and sensitive detector inheritance, otherwise Jean 4 kind of gets confused. That also involved that the physical volumes needed to be stored, that I can find them in the stepping action. I needed to propagate the T-tree downstream, so Jaroslav does this with inheritance and the base class. I removed the base class, so I had to basically get the T-tree into the downstream. And basically I replaced the detector construction CXX by a G4L Mon detector interface. And I dropped the G4 messenger, and I dropped the input reader. And in the hope that, okay, whatever he's using as an event generator is covered by EIC smear. So I didn't try to read in the input. Could have done it, but I was kind of too lazy to write that code. So all in all, it's actually interesting. It basically resulted in 20 lines changed in his CXX files and 8 in the include files. There was some missing declarations, and I had to tweak on the Jean 4 include path. But in general, that's all there is to it in the end. So the original code you can find here. The fun4all base code is on that side. So, okay, now let's run this thing. Okay, I'm here. There's nothing. Now I need a mouse. And everybody with a laptop or working, you probably want to do the same. Okay, so here I'm cloning the detector area, and then okay, the next ones I'm not gonna. Okay, so I'm gonna go down there, make a build directory, go to the build directory, run the autogen, which I'm gonna do just now. what this does, it basically creates a makefile in the end. So it runs configure, creates a makefile, and during the make install, it will create these $home my install directory in basically my home area. As I pointed out, when you have a private installation, you have to source the setup local script with your install area. Yeah? And this is just to print out how your LD library path and your path looks like right now. If you would print out the root include path, you would get like 2 pages of it, which is why we kind of hid it in a script. Okay, now let's go to the macros directory and start running the show.
Hey Chris.
Yep.
Whenever we do this first step, we get a couple of command not found errors. Is there something else about the environment we're supposed to set? The very first command in example 0, the source.
This one? Did you do the -n?
Yep.
We are on RCF and we can't access the CVMFS.
Whoa.
While on the contrary, I'm not able to run the autogen. It's giving error.
Okay.
Do we need to have a Phoenix account on our
No.
Is there any sensitivity to whether you're in a bash shell or other shells?
Oh, right. Thanks, Tom. My mistake. Wow. You've done this before. Okay, so sorry. We support 2 shells. Yeah? Bash, which is the easier one and the one I can really recommend. And there's the C shell, which normally all the RCF accounts use. So what you need to do, awfully sorry, I really should have mentioned this, instead of SH, do CSH.
But nevertheless, I mean, bash shell.
Okay, that works.
And then also here, this one also a CSH. Yeah, so whenever you see an SH, put a CSH there. Yeah.
I mean, the bash shell, I don't know if it is my install, the prefix. Not working, but it
Could be minus prefix. There was actually
and that sounds.
Yeah. The problem I had when you just type this into a web page, it comes out with a character which is not interpreted as a minus on your command line. So this is with code and /code. Normally it's minus prefix, and when I tried it, this worked, but try minus prefix.
C++ compiler cannot create executable.
Whoop. Did you source this one?
No, this I don't, since I told you before that I do have problems, but I can. It's
working now.
I can try.
Yeah.
I can try. Maybe I
Try the
Sorry to interrupt you.
Yeah, no, it's fine. No, it's again. If you guys send me emails, I can look into these things before tutorials.
The install is working, so this is a good
Does
sign.
something need to be different for running on my laptop?
Not really. I mean,
doesn't find stash.
on your laptop, what?
You need to have a CVMFS.
Yeah. Did you run did you follow this
I'm in Singularity.
in your Singularity? And did you start it with -b cvmfs /
Did everything in the Phoenix environment. This doesn't.
No, I don't have the.
on your laptop? So what you need to start it with. Basically, this is how you have to start it. If CVMF, Jim can actually help you. Thanks.
In the Singularity, I don't have a CVMFS.
No? Then there is over here. you can from here you can download these update build .csh, which basically makes we have tarballs of the CVMFS distribution, and that basically you run this and it basically installs the stuff locally on your system, and you can mount it then as a local directory.
I can go out from the Singularity and try to run directly on my CentOS and see.
That should actually work. I mean, depends what packages are installed, but it should work.
Okay. So sorry. Please go on my okay.
Yeah, that's right. Right behind.
Let me see. Okay. Everybody here? I mean, things sort of compiled?
Yes.
Whoa, come on, you're going ahead. That's not fair to the other ones. Okay, so what you do next is you basically start up root. And all the so let's have a brief look what we're actually executing over here. How these macros look like. As I pointed out, they always have root 6 section on top, and then continue with down here. From here on, root 5 can digest them. Again, in the future, do yourself a favor, and don't try to be compatible with root 5. So basically, this is how one of these macros look like. So you get an instance to the server. One thing which is very handy, it's not being used over here, is we can actually also nail down the random seed. So we can, whatever we're doing, we can make it reproducible. For debugging, it really helps when you can reproduce things. And we make sure that the seed is propagated everywhere, so you can produce identical simulations all over the place. Ignore this one. So what we have our own little implementation of the particle gun. So what I'm going to do, I take a gamma and a pion at 1 GeV over C in Z. Set the vertex to 0, 0, 0. This sets the gamma is also 1 GeV. Just making sure these things actually hit the tagger. I register the gun with fun4all, so it's actually being called. Down here is the Jean 4 setup. So again, I get my PHG for Rico. That's the interface. By default, it has a magnetic field, so I turn off the magnetic field. It saves the geometry you're using in a GDM file, that you can read it back into root tgeo, so we don't need this here because it takes some time, so we've set this to false. Okay, now here's Jaroslav's subsystem. So it's the Lumimon. I register it with G4Rico. Then I tell fun4all to run G4Rico. So I register G4Rico with fun4all. That's my input manager. And again, since I'm using the particle gun, it's just an empty event loop. And as an argument, I can give it the number of events. 0 means run over all events in the file. If you run 0 with the dummy input manager, it runs forever. So we have a little check in here. I run over the number of events, then I have a little printout at the end. I call fun4all, telling, okay, the show is over, save your histograms, do whatever is needed, print something out, and then delete the server to clean up. Oh, as you can see from Jaroslav's code, so it actually opened his root file already here. Oh yeah, and running with using -1 as the argument basically doesn't start the event loop. It basically just sits there now. It's very handy when you want to do detector displays. Oh, come on. Now what? Hey. One little hint, root understands tab expansion. It's very, very nice.
Yes, I do have another question.
Yeah.
So on my, if I go out from the singularity, I was able to configure and download the code, but then I do have some problem in the making.
Yeah, that's because it uses the system packages for that, and if they're not installed or not the right version, then...
Which compiler do you use?
It's 4.8, but it should be...
I'm using 6.3, probably.
Oh, okay, no, that's not going to work with the environment, because all the... I mean, it might or might not. It would need to be, need to be tried. It should compile, everything we have compiles with GCC 8.3.
Yes,
so...
in principle, but if you have other codes... or configuration. And Okay.
Now again, this is exactly the reason why we say we do this in singularity. Because
that was the reason why I was starting the singularity. But inside that, I don't have the.
Yeah, but this is also why I sent a mail about yesterday that people should do this and not come here. Okay, so as you can see over here, that's Yaroslav's detector, and I have a little messenger in fun4all, which basically just implements the run command. Okay. And it takes a while. All right, here we are. As I said, we have there's a photon and a pion coming down the beamline. The pion gets deflected by the magnetic field in here. So as Jaroslav pointed out, there's a magnetic field. So the magnetic field's implemented. Yeah, so you see the little red one is the pion, and the green one is the photon, which then hits the detector over here and does something. Yeah?
Can you repeat the comment that you put in?
Oh, sorry, sure. Yeah. So this is basically, I implemented a little messenger into fun4all where other commands can be added. Right now, it only understands the run command because I wanted to be able to show events in here. There is another way in fun4all, which is actually in the end the preferred way, because as soon as you get into more complex detectors, this Qt interface takes basically forever. It's easy to sit in front of it for an hour until it displays something. So what we have is basically pops up this, and you see it's a lot faster. And you keep the command line. In the Jean forward, you lose it. And the reason for that is that Qt refuses to run in a thread. It wants to run in the main thread, which then interferes with everything else. And poof, again, here's your pion, and here's the your photon hitting something. So that was Yaroslav's Luminosity Monitor. So now the question naturally is, oh yeah, right, we have a new framework, cool. Why don't you just rewrite everything you did? Why don't you just come? And so what's in it for him actually? That's always the good question. You know, you get access to all implemented generators. That's nice. You know, he can keep everything. You know, he can keep using everything he developed downstream because the output file hasn't changed. And okay, less code to maintain, so there is no, you know, no G4 messenger, and I think that was about it. So the question is, yeah, you know what? Again, if somebody would give me this and tell me I have to change all my code, I would basically say no, I'm not going to do that. Okay, but now in the new framework under fun4all, he can actually. It's not meant derogatory, so just point this out here. The code's good, so don't. So you can play with the big kids because detectors are added on a macro level. And basically, what I did, I took our EIC detector implementation, which is a full-blown collider detector, and put Yaroslav's photon tagger or luminosity monitor in front of it. So that works, at least on the display, so we can do it. They're together in the same G4 simulation now. Naturally, there's fine print. Since the stepping action he uses is different, it does not put any objects on our node tree. So he leaves the cat litter outside somewhere. It does not include, but that means you cannot include the detector into any fun4all supported analysis chain, construction code. Definitely, when you look at this, that's his vacuum box, which goes straight through the EIC detector. There are overlaps, so which need to be dealt with before you can actually kick off a reasonable simulation. So you need to deal with those, which would basically mean in this case you would cut off the vacuum box over here. Just make sure you connect here. There's a beam pipe in there that you connect there to the beam pipe to keep this nice and vacuum over here. And as I point out, our world in our detector is filled with air. That's very nice for people to work on the detector, actually. The technicians would hate that if you would evacuate everything. So what you need, if you have something forward, you actually have to have some kind of vacuum system to beam pipe something, to basically get vacuum to your detectors. Yeah. But that's basically with 20 lines of change, you get this. So that's a good carrot. Now, let's get over to use fun4all for real. So this is not a test. So rehearsing the program flow with in Yaroslav's example. So what we basically did, we have the fun4all server. We have an event generator that was the particle gun, which put a photon and a pion into the G4 particle stack. We had G4Reco, which basically had an interface detector which talked to G4Reco. I copied over his or basically I reused his construct method in his detector implementation, and I needed to tweak something on my infrastructure that basically I call his stepping actions, which does the hit extraction, and then it goes from there directly into the output file, just like what he wrote. So this is basically what you saw just now. So, now in fun4all, as you remember, you basically, if you implement a stepping action which puts the data onto the node tree, you can actually proceed with real data reconstruction. So you're basically right in the data stream with everything. Yeah. So let's see how this looks like when you do this. A little word, G4. What your code gets is a so-called G4 step, which basically says, okay, it propagates the particle until something happens. Could be a decay, could be an interaction, could be volume boundary, could be volume entry. So what you get is basically steps and the energy deposition within that step. And after each step, the user stepping action is called with a pointer to the current step, which then, as you also pointed out, has all the information you ever need. Energy loss, particle momentum at the beginning, at the end of step, scintillation light if you want to, ionization energy, you name it. Daughter particle, parent particles. So you've got the whole information over here. Okay, but if we would basically save this, that would cause that would be a tremendous output. So what we are doing, we have something which we call G4 hit, and you're going to hear this a lot. What this basically does, it takes the entry of a volume and the exit of a volume, and it integrates the energy loss over there. So what your G4 hit has is the coordinate of the entry volume, of the entry point, the exit point, or if it decays or stops, at basically when it stops existing. And the integrated energy loss. And also our hits are kind of flexible in terms of what you want to save with. For calorimeters, for example, for scintillators, you want to keep the scintillation light, so you can save that one as well. For a TPC, for tracking, you want the local momentum at that point, so we save that one. So we are flexible in what actually goes into G4 hit. But it's always entry to exit. Naturally, for the TPC, we can also save single steps if we want to, but this is basically the standard what we're doing. And okay, as I pointed out, we keep the ancestry for the G4 hit, so anything can be traced back to a single to the primary particle. What we do in terms of cleanup, when you store, especially in calorimeters, when you store all the particles generated in there, you will find that your memory and your file size basically explodes. So in order to reduce the size of the output, we don't store particles which do not leave any G4 hits or are not ancestors of a particle which leaves G4 hits. So particles we cannot detect and whose daughters we cannot detect, we don't store because it doesn't make any sense. Okay, now coming to our node tree. So this is our access to data objects. It's basically a standard tree structure. You have some top node. You have 3 different kinds of nodes. So you have composite nodes, which are nodes which contain other nodes. You have called PH data nodes. I'll get to the distinction later. And you have PH IO data nodes. The IO data nodes are the ones we can actually write out. So since we use root to stream out those data, there needs to be some, root put some restrictions on what you can actually save. So they have to follow some restrictions from root in order to be that we can use them as IO data objects. The PH data nodes could be any class you ever want. So it doesn't even have to contain data. If you want to put a reconstruction object there, which you shouldn't, but you can. So you would basically call a PH data node, and it would basically just sit there happily. Okay, now coming to the node tree itself. So it's as I pointed out, it's not a root T tree. So it's basically it's the way we organize our data and make them accessible to modules. Here's again, we have these 3 different kinds of nodes. The PH composite nodes, so the ones which contain other nodes, and PH IO data nodes, they can be saved to a DST and read back. So you can basically, this stuff you can stream out to a file and read back, you get the identical structure. The DST itself, so the file, that actually contains T trees. As I pointed out, this is why there are some restrictions on what you can store in a PH IO data node. And the node structure is saved in the branch name. So that's like the little trick. So we don't really save the IO data nodes as separate data objects. They're just coded into the branch names. Root's limitations, that's more meaningful for root 5. Root 6 is not as piggy, although in root 6 there are also some cases where it can't deal with it. At that time, root 5, anything containing boost, for example, was off limits. What we do, we save 2 root trees in each output file. One contains the event-wise information, and the other one the run-wise information. If you basically put everything into the same tree, you would have to store the run-wise information for every event. So this is why we split these things. But again, this is transparent to the user. You don't see anything. You get your node tree in memory, just like you saved it. And our input managers, they basically take these IO data nodes, put them on the node tree so that you can work with it. The output managers, they save, you can select certain nodes to be saved, Yeah, they basically dump these things into a file. And for later on embedding, this gets important. We can have manage multiple independent node trees in memory if we want to. So for embedding, for example, we have the foreground event, the background event, and the mixed events. You can basically, if you have 3 node trees, it's kind of easy to manage. You can copy these things around easily. So node tree itself, so it starts with the top node. So that's just the default. And creation and populating of other node trees, okay, as I pointed out, is possible. You can print this out at any time. You get during startup, you get a printout of what's in memory of the node tree, but you can print it out at any time with this little command over there. Yeah. Here are 2 trees which are important because they are the ones which get saved on the file. The DST node, under the DST node is the event-wise information. And under the run node is the run-wise information. What the framework does, coming back to I love the litter box, I'm sorry. So under the DST node, they're basically reset after every event. So basically after every event, fun4all cleans up the litter box that events are not mixed in memory. Yeah? So that's what you really want to avoid, that you keep information from a previous event and then pollute some following event. So everything in here is clear, is reset after every event. If you want, if you want to, you can basically, the ones you save, you can reconstitute them under a different node tree if you want to. Yeah? So again, you can have separate various different node trees in memory. If you feel like it, you can add your own composite nodes here directly. Nobody stops you from doing that. What you see in our code, we have something called a power node, which contains more complicated geometry objects, which we actually don't want to save on the DST. So what we save on the DST are these guys. So we've got here this for the beam pipe, the parameters. Here's actually the geometry object for the beam pipe, which contains things in a way which is more suitable for accessing it with code. And the power node is not being touched by the framework. So that's absolutely under your control. Now, if you print this thing out, it actually gives you some information. It tells you, for example, this PHD for in event, that's a data node. So that's something you cannot write into a file. IO, these are IO data nodes. So these guys you can all save on the file. It also gives you the class of the object which is being saved. That's later on important when you say, okay, I read an analysis module. You have to know the class which was actually saved, and this is where you get the class name from. Oh yeah, one little caveat. Everything you put under, your code puts under the node tree, everything, including power nodes, homemade ones, you lose ownership. So what fun4all does at the end in the cleanup stage, when you delete the server, it basically goes over the node tree and deletes everything. If your reconstruction modules deletes this node, you get a nice segfault at that point. So it's basically a consistency check, clean up there. So if you put a node tree once on an object on the node tree, don't delete it, you lose ownership of it. You can fill it, you can do stuff with it, but don't delete it. Okay, now I talked a lot about analysis. So how does your analysis module actually look like? So again, we have a base class. Remember the C++, you have to know what a base class is. And it basically gives you the methods which are called by fun4all. So if you don't implement all of them, perfectly fine. They just don't do anything. So what do we have? We have six methods. So you have an init method, which basically, initialize yourself. You have some start, your reconstruction module, you make a new one. Okay, you want to be initialized. And you want to have maybe the node tree as an argument to figure out what else is around. So this is called once when you register your module with fun4all. Then we have an init run method. This is more coming from the raw data reconstruction, where you basically have the concept of run numbers, which means that for different runs, you need different calibrations. So you want the module to be called to load up-to-date calibrations when the run number is known. So again, for the simulations, that's not really relevant. Process event, guess what this does? Gets called for every event. And again, the node tree comes as an argument, the top node. So you can you can navigate the node and pick out whatever object you want. Reset event, that's called after the process event for every module was called. So this is, sometimes you have stuff in your reconstruction module you want to reset before the next event comes. Yeah? So that would be the place to do that. We have an end run, so there is, again, from the data reconstruction, there is a possibility to run over multiple runs if you want to, but that means your module wants to be called at the end of a run and at the beginning of the next one to load calibrations, and the end of the run to maybe save some output again. So this is what this is for. And then there's the end method. As I pointed out, this is typically used to flush out histograms. When you say, okay, now let me save whatever I have and do stuff before I quit. Again, if you create another node tree, you can register your module with a different node tree. So then your top node is then the secondary node tree. So, okay, now how do you navigate this thing? Which is in every argument. So here's, for example, we have a node that's our inner calorimeter. So that contains the G4 hits of our inner calorimeter. And this is, where the printout comes in handy. So here's just, here's the process event of, my analysis. And to get to the G4 hits, so I know from the printout, remember, it's a PHG4 hit container. So I'm going to get a pointer to this one. And then there's a template get class. You need the type of the object. So that would be, again, this one. And that's the name you saw from the node tree printout. So this is basically how you get to these things. If this node doesn't exist or the class is wrong, you just get a null pointer. So you might want to put a little check in here just in case there's a mistake somewhere. And just a caveat, this thing will it will traverse the node tree and it will return you the first node with the name it finds. So if you have few nodes with identical names, which is a really bad idea, but again, you can do it, this will not work for you. So then you can hand navigate the node tree if you want to. So my recommendation is just don't use identical node names. You'll make yourself very unhappy. Okay, now let's see, how does a simple detector with hard-coded geometry looks like? And yes, it's a box with a half pipe. I want you to see how these subtracted volumes, how they look like. So the GitHub location is in the example detector. We have a source and macros directory. And, it's over here. There's a code which actually then dumps this data into an n tuple, just for reference. So, okay, now let's start up this thing again. All right, so what we do, the first one is not necessary. It's just, if you want to reset your environment from time to time, you can execute this as many times as you want to. It basically refreshes your environment. It removes your LD library path, whatever you have added. It basically resets everything. Yeah. So I'm not going to execute this, but we should go back to the top directory or to your. There we are. Okay. Okay. And as you can see over here, I'm just dumping the whole thing into the same installation directory. Okay, let me just show you what we do in the installation directory, because that's so there's a lib directory. You can see Yeah. This is the stuff we just compiled. This is Yaroslav's code, so it lives happily ever after there. What we do with our include files, you have to install some include files, and I can only recommend this. You'll find in the make file that we actually create subdirectories for those. Again, there's a favorite game of users cut and pasting code and then overwriting each other's include files. And then since root 6 now actually uses these include files, you get really, really strange errors when this happens. Yeah? So, try to keep the install directory, the include directories, use the example, how this is being done, so that they end up in separate subdirectories. Wait, where's my example detector? Okay, let's see what we actually just built. So let's start with a subsystem. So that's the interface into PHD for Recon. Yeah? What you see over here, it has also an init method. It's closely related. Basically, it's mirrored after the analysis module. So it has an init method. It processes every event, but it also contains a pointer to the detector implementation. So we keep this in a separate source, and a pointer to the stepping action, which again we keep in a separate source. And you can see down here. So we have got two more classes: the G4 example 01 detector and the stepping action. Well, let's have a look at those. So first at the detector. This one is really, really simple. So here, that's basically the G4 construct method. It turns out when you want to have a volume hierarchy, we have to intercept the construct method and then dish it out, basically pass the mother volumes down here if you want a volume hierarchy. Yeah? So this is why otherwise it could be the construct method, but then you would basically register with a world volume right away. So if you want to have a volume hierarchy, so this is why this is called construct B. Otherwise, this method is identical to the construct method. Okay, let's see what we have. So it's a cube. Yeah, I guess that was pretty obvious. 20 centimeters side. So we make a box. Then we make a little cylinder, quarter of the size, and go half pipe, so from 0 to pi. Then we take the box and we subtract the cylinder from it. So call this whole thing hole in the box. Then make a logical volume out of this thing. It's aluminum. This is, I guess, why it's gray. Give it another name. No, actually here we make it gray by hand. So we give it the attributes. So we give it the color gray. The idea is that you can actually see the tracks on the display. So that was brilliant. If you have yellow, then you can't see the photons. Yeah.
I have a very quick question. So the actual hole that you generate, are you able to fill that with a material, like to define air, vacuum, whatever?
That is a very good question.
Yeah, so if you're trying to make a magnet with a bore and you want to put vacuum inside of it, for instance.
Yeah. Alex, I think you can, but I probably forgot here.
The hole has material ceramic volume, so if this shape is in air, the hole is not just in air like everything around.
Yeah. Okay. Thank you. So it's air.
Ooh.
Why is that?
Why is that?
If this shape is placed to dot volume with air, then the hole inside has the air like the air is outside. If this is placed in vacuum, then the hole
I don't
right.
see.
No, yeah,
but I think you are extracting it from the main body.
Yeah, exactly. I mean, I think what happens is that you subtract the volume from that. Yeah. So what you actually take, you take a block and you drill out the hole. With that, it becomes part of the surrounding volume.
So if you wanted to put a vacuum inside of it.
Oh, then I would have to put another tube in there.
Okay.
So then I would have to use. I think there's added there's volume added and
differences. So if you're doing a magnet, you would add a beam pipe filled with vacuum in that case.
Yeah. Mm-hmm. Yeah. So there's this what's the G4, what's the solid thing, subtraction solid, then there's a union solid. So there's a way to do that. Good question, thank you. Okay, so I basically say, okay, now I actually want to have it displayed, and set the visual attributes, and then I just put it here at the center. We have a little thing in our system which basically checks for overlaps according to some variable we set, just to be able to occasionally check if our detectors are overlap or not. And then what is needed in our system is that the physical volume, we basically, in the stepping action, we need, the way this is implemented, the stepping action is called for every step. Every stepping action is called for every step. So basically, the first thing the stepping action has to do is figure out, am I actually in my volume? If not, you just return. If yes, then execute the stepping action. In order to be able to do that, we basically save the physical volumes in a set over here. And up here, everything has, an is-in detector method where, you basically, the stepping action calls you with a given volume, and you see if you're inside the volume. If yes, then it's kind of a Boolean, return 1, if no, return 0. Yeah. Okay, now the stepping action is a handful. The story behind these things have grown over time. Jean actually does have bugs. Strangely enough, it actually does. So quite a lot of the code in there deals with problems we encountered over the years. For example, when you had electrons hitting a corner, all of a sudden this thing ran into basically gave you hits which just couldn't exist. So the stepping action contains quite a few checks here. But basically, this is what Jean requires. So it basically hands it down a step, and you basically return if it was used or not. I'm actually not sure if Jean uses that information. So this you can see here is we basically get from the step, we get the entry point and the exit point, the beginning of the step, the end of the step. We get the physical the volume where the step happens, and then okay, we test, are we in our detector or not? And if not, then we don't use it. Okay. So further down, the good news is you can cut and paste most of the code. So this is really, it's identical for all volumes except when you say, okay, I want to save additional things. Then you basically have to further down define what you actually want to save for it. What do you want to extract from the G4 step and what you want to save. Yeah, this is one of the debugging things. So okay, so this is now our, we make our hit over here. We have a concept of a detector ID, so that when you have multiple detectors together, you can basically put them into one data object and afterwards ask the object, okay, from which detector does this hit actually come from? We save the entry coordinates, we save the time, we save the Jean track ID. That's important for the truth tracking, and down here we sum up the deposited energy and the ionization energy. We initialize it to 0 because that's the thing you need to integrate. Then lots of blah 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 blah. And okay, this is the condition which tells us that okay, this basically we leave the volume, or the track has died, we leave the world, it came to a rest, or something killed it. So that's the certifiable last step in a given volume, last step from this particle in this given volume. So what we do, we integrate the deposited energy upstairs. We set the exit coordinates of the hit or where the particle died. We set the time of the exit. This is again related to the truth tracking. We only set these tracks to that we want to keep them if actually the energy, as I told you, the energy loss is larger than 0. So they integrate the energy loss, because again, if a particle didn't leave energy, you just cannot detect it. So why keep it? So this is for bookkeeping. This is information is later on used to discard particles which basically don't leave any trace in the detector, and which daughters didn't leave any trace. We have a special handling for giantinos, which will be important for this example, because giantinos, as you know, they don't leave any energy, they don't do anything, but we certainly want to keep them for giantino scans. So the giantinos are handled separately, and since the energy deposition 0 has a certain meaning later on in the code, we discard it, we set it to -1 just to keep it. And that also tells us later on in our output that, oh yeah, this tower was hit by a giantino. So makes our world downstream a lot easier. And that's basically it. At the end, you basically, when you're done with the hit, you reset it and basically next.
Chris, can I ask one more dumb question?
Sure.
Earlier in the code, you have a differentiation between active and passive material.
Okay.
How does that relate to a sensitive volume? Because if I have a material where I want to look at secondary production, like for a background or something.
So we do have the concept that complex. I mean, not this one, but complex detectors, they have active and passive volumes. Like calorimeters, you have scintillators and tungsten powder. But in certain occasions, you actually want to read out the passive volumes as well. And the way we do that is that we say, okay, we basically decide in the detector setup, in the macro, we say, okay, the absorber should be active or not. And this is what the switch active goes for. So often we set both to active, then everything is saved. If you say, okay, I only want the scintillator, I only want the active material to be active, you're not saving any of these background hits, which again, in calorimeters, it makes a huge difference.
So in the passive material, you'll still get the stepping and secondary production, but you won't save some of the information at the end. Is that the difference?
Again, the stepping, it's again up to you what you do in the stepping action. So what this thing does, it really just extracts these Jean-4 hits and puts them on the node tree. We do have Cherenkov counters, which do something with optical photons. So yeah, there is some analysis inside the stepping action. Not too familiar with it. But again, the stepping action gets handed to you. You can do what you want, and if you decide, okay, I want to basically save a separate data object, fill something for myself, you can, push that on the node tree. So that's possible.
For the geometry, that's fine. If you wanted to change it, seems like right now it's in the source code, so you have to recompile. But is there any of this like GDML?
Hey, that will be for the next tutorial. No, so in principle, this is the most simple setup. What we have, I told you about the cylinders, for example, blocks. You can basically tell them, where they are, what material they are, rotation, translation. So you can do that. We have interfaces into GDML, so you can give them a GDML file, and the detector will be recovered from that. For example, for S-Phoenix, we use the ALICE inner tracking detector, the MAPS detector. And we basically just have a GDML file from them, and that basically gets read into our simulation. So that then basically boils down that you have different kind of detector, call it types. It's not just cylinders. In this one, we have one which can you give it a GDML file, and it pops up the detector inside PHP for Rico. Where then you have to then translate the sensitive volumes. You have to do some text lookup to figure out, okay, is that volume actually sensitive or not, or is that support structure? Actually, thanks to Alexander, we can actually now read CAD files. That actually really works nicely. So we can read a CAD file and make a GDML and basically get this in our simulations. We use it for our TPC for the end caps. Okay, where was I? Nope. Okay, so let's just build this thing quickly, or run it quickly. So I'm not going to go back to the page because I kind of know what. here we are. We can rotate it. So yes, the detector is there. So now I can shoot a pion into it. Whoa. So what do you do with this? Not much. Huh? You can put another one in. Get a bit more splashes. Fairly meaningless if you look at it, right? So, I mean, yeah, we can shoot a pion in the block of aluminum. But what you want to do, you actually want to do a bit more than that. Okay. So, for example, one question which comes up frequently when you put, especially after all these rotation translations, okay, after all those rotation translations in your code, again, this was a simple one. In the end, you kind of lose track. Do you actually know where your detector really is located? Is it really where you think it should be? It's because Jean-Fort doesn't really tell you. I mean, it puts a nice thing into black background. And you're like, fine, is there an overlap or where is it actually? Also, the size of the detector. I had a typo once. I think I built the world's largest silicon detector for a while. It was like 1 kilometer long. Did really well in terms of coverage, but so again, how do you verify that? So and now remember the G4 hits where we said, okay, you save the entry hit and you save the exit hit, and we actually can detect, basically look at Giantinos. So what we basically do here, we just run 10,000 Giantinos in spreading them around a bit, and have a look at the entry and exit hit. Let's just do this. Oh yeah, and by the way, for people who don't know what Giantino is, it's a non-interacting Jean particle. There are actually charged Giantinos now, and the discovery announcements typically April 1st. You read somewhere in Fermilab or CERN that it has been discovered finally, but so far it's yeah.
So yeah. In fact, the charged Giantinos would be the only purpose of using particle for this. So I realized myself with surprise that you can get pretty much the same information from the navigator itself. Just shoot through the material without any particles. Yeah. And it's a script like that. Yeah. I can send something.
Oh. Okay. Let's go back over here. Okay, yeah, we've done both of these. So now let's start root and start the. Okay, and now the argument tends to be, the first one tends to be the number of events you want to run. Giantinos luckily go pretty fast. The EIC is the output of the node tree, which gets printed out at the begin run. So you see, okay, that's our hole in the box, and these are the G4 hits from our hole in the box. And it's a PH G4 hit container, and that's the name. So if you look into our hit and double code, I'll get to the macro just now. You can actually see this. So. Now let's analyze this. Little trick, if you plot the exit hits first, because the exit is on the outside of the detector, if you put the entry hits first, you basically get the entry hits, and the exit hits are outside of the outer dimension histogram. So this is why I'm starting with the exit hits. Just to mark them differently. as you noticed, I've done this before. So now we can twist this a bit, and here, look, here's your hole. Entry hits, exit hits. So I put the Giantino source kind of right in the middle and just sprayed it on for 2 pi and a bit in this direction in Z. And the nice thing is down here you actually have absolute coordinates in centimeters, so you can actually kind of verify that it's centimeter range and sitting at the center and is basically where I think it is. Okay, the other thing I told you is that in fun4all you can actually save the analysis at any stage and reading it back with a separate macro. Not sure. How's my time? Oh, okay. Let's speed it up a bit. So I don't. Again, if you run these macros, you basically get the same plot because I think I nailed down the random number generator. One thing to note is that this is the macro which reads the DST, and if you set it to 0, it goes over all the events in the file. So that's an easy one. The nice thing is that in the G4 DST macro, so this one, which actually generates which runs the Geant 4, it doesn't have any analysis code dependence in this macro. So that's completely separate. And in the readback, you don't have any Geant 4 dependence in the macro. So basically what this means, DSTs can be created by somebody somewhere, and I can read it without actually having the code of that person or the detector implementation, as long as they're writing out G4 hits. Okay, just briefly, since I promised the end tuple. So that's my analysis module, which creates the end tuple. So here, remember the init method, which is called doing startup. So I'm making myself a histogram manager, again, not to lose the end tuples and the histograms when I open another file. So I recreate it, and down here, this is all there is to it. Remember in the printout, it's a PhD4 hit container. Okay, sorry, I coded the node. This contains the node name, which is hole in the box. G4 hit and then hole in the box. If this thing exists, loop over. This is the way to loop over all the hits. So we have some type defs which basically do this for us. So this is how you loop over the hits. And then this is how you extract information from the hits. Yeah. You fill the end tuple. Yeah. And at the end, you basically save your end tuple and tell the histogram manager to dump the histograms into the same output file. And that's it. Yeah. So basically what you're dealing with in our code most of the time are these kind of constructs where you just have an iterator and you just loop over, basically use this iterator to access the, whatever, tracks, hits, parameter clusters. So they all look alike. Makes life a lot easier. All right. So that was nice, but now in your design stage, what often is the question? You want to design kind of an inner tracker or some tracking detector, and so the questions always comes what's the momentum resolution? What's the distance of closest approach for tracks to the vertex? Naturally. Especially professors are good at that. Can you do better? I don't have to put in the work you do. So can you do better? And the last question is then, have you any idea how much this costs? How about, using fewer layers? Is there any possibility to, remove a few layers? And okay, welcome to our, Geom4 simulation with a Kalman filter-based reconstruction and vertexing. Yeah? So what you do, you put a detector together from simple shapes in a root macro, cylinders or boxes. You pick your particle and, your momentum or, a couple of momenta. Tell the tracking the error on the hits, so basically the granularity of your detector. Yeah, and then watch, rinse, repeat until you like the result or until your boss says, okay, it's good enough. I think you trust me that we don't have to display this now because we're really running out of time. So the example here is it's a 6-cylinder silicon layer with these radii, from 2 centimeters to 63 centimeters. That's the thickness of the silicons. And what the example is doing, it uses 4 GeV over C positrons. Yeah. And what we need to check out is this macro. So. All right, you need this command to get the macro. The nice thing that goes quick. As you can see, this is purely done on the macro level. You don't need any code to compile. And here's the command line that you can actually do everything at once, so you don't have to fire up root and type all these things. You can just do this in one shot. So. Okay, let's have a look at the macro, what I just did. So, okay, we have a particle. It's one of our particle generators. It basically makes a uniform. You can basically tell it, what kind of particles we want. So positrons, put the vertexes 0, 0, 0, give it an eta range in which they are distributed uniform, and we want to kind of have it really at the center, from 0.05 to minus to plus. The momentum range, so 4 GeV over C. And okay, from 0 to 90 degrees, that's not really important because this whole thing is azimuthally symmetric. Okay, we are using a 1.5 Tesla solenoidal field for this whole thing. And here you can see that's the thickness of the silicon detectors, the radius at which they are. This is the length, which is not important here. It's just, they cover the range in Z. So what you do in the macro then? Okay, you basically say, give me a, for each layer, so 6 times, make a new cylinder subsystem. Yeah? That's the name of the thing. You will find the G4 hits under this name. The layer number is identifier. You set the radius of each one, the material, silicon, thickness. You tell it should be active. And the super detector just says, okay, put everything into one output object, not generate 6 different output objects on the node tree. And register it with a G4 Rico, and that's it. That's actually another nice feature we have. We have a detector set up, or we can basically change every detector into a black hole, which means any particle going in never comes out. So they get intercepted right at the stepping action and terminated. And the energy gets added up. So if you have a colorimeter and you want to see leakage, you surround it with one of those, and you basically see what ends up in the black hole. You know exactly what kind of energy goes out.
Which macro is this, please?
Oh, sorry. It's the, yeah. Yeah, sorry. Yeah, let's go back here. That's the. So let's see in the tutorials. So we have the momentum section there. Yeah. And the macro name is fun4all G4 momentum. Let's see. You got it? Okay. Okay, because what's interesting comes here at the end. So this is now our fast, common filter. What this basically does, it takes the truth information. So it takes the true Geom4 hits. So it doesn't do any kind of tracking or so. It basically takes the Geom4 hits from a given particle, from a given track, and fits them using a common filter. Yeah? So what you basically tell it over here, this is, remember we call this SVTX. So we tell the common filter this is the nodes you have to go for. Yeah? And that it's a cylinder, so we also have, I think we have cones, so we can actually do forward tracking with it as well. And then the radial resolution in centimeters, so that's 300 microns? I think so, yeah. And azimuth resolution in 30 microns, Z resolution 1 centimeter. So it's kind of a silicon strip detector, what we have over here. And further down, this is an evaluator which then generates the basically generates the n tuple with the evaluation, with the momentum resolution with these things. Huh?
Chris?
Yeah.
Do you have the possibility to input the maps of the magnetic fields, so to have a more realistic?
So what we can do, we have one basically global world field map we can put in. Again, over here we said it's a constant solenoidal field, but at that place you can put in field maps if you want. Yeah. So I think I ran this macro with a thought. Okay, so here's the n tuple already. Okay, so let's have a look at the momentum resolution. Yeah. So what this is, px, py, pz is the behind here. That's the reconstructed momentum, and gpx, that's the Geom momentum. So we're looking at the bt resolution. Okay, obviously there are some really low-lying guys. So let's restrict this a bit. Yeah. Oh, that's basically, for this detector, your momentum resolution for 4 GeV positrons. So the mean is slightly lower. I mean, you have energy loss in the silicon, but that's not too bad. And
is this accounted, or in the fit? Is this accounted?
No, the fit? No, this is just what GenFit says is the momentum of that track in this magnetic field. That's what. Yeah.
So it's not the Kalman here on the hit.
No, it is a Kalman filter on the hit positions, but it basically reconstructs a mean 9 point.
What I was asking if it takes into account the average energy loss in the silicons in the fitting.
Not sure. Jen? Yeah, sorry.
Yes, taking into account the full Kalman filter. And other end of simulation, the geometry and the magnetic field map is automatically importing into GenFit 2. And the GenFit uses.
Okay, so it's accounted.
Yeah. But there are hard radiations which lose.
No, of course, it's on average. So you cannot get the full energy, but you recover most of it.
What you might notice, it looks actually pretty good because what the example detector is actually kind of one of our optimized ones. Yeah. So let's just show the DCA. So just distance to closest approach. We can also get out of this. Yeah. Also nicely centered. Okay, since I'm Again, running out of time. Okay, let's hope we can see that. Yay! So now, again, the nominal one is actually, that was optimized at some point. So this is why this looks really pretty good. I can mess these things up really badly. So if I just put in silicon, which is really thick, factor of 10 more, hey, look what the radiation tail does. So we can get these things. The DCA also kind of, suffers quite substantially. I narrow the layers down. So I basically say, okay, I basically divide all the radii by factor of 2, just half of the layers, bang, there goes your, that's the momentum resolution for, if your outer layer is 30 centimeters away, and your DCA doesn't change too much. And then finally in the Kalman filter, I'll say, okay, fine, let me, reduce the resolution by a factor of 10, so make a really big pixels. And so your resolution goes to hell. So yeah, so this is something where you can quickly, easily, determine the momentum resolution of your design. So it's kind of important before you run any, tests or build something. Naturally, coming back to cats, as a graduate student.
Who is this unfortunate animal?
The unfortunate animal, you see, what we just did was basically generate one data point at 4 here for positrons. If you really want to do a decent measurement over all the momentum ranges at all etas, you're basically, let me say that. This prospect, is basically, should motivate you to learn about programming loops and running batch jobs. You don't want to run this interactive. Okay, now adding detectors to existing setups, coming back to Jaroslav's first example. So here again, the commands. Again, you don't use Qt. We probably should be able. Okay, that's something we can do in the break because that really runs long. Okay, now how do I actually really add Jaroslav's detector into this thing? So so if you check this out under G4 simulations, you basically find our big detector setups, where basically you find that's the EIC detector. So they're basically each consists of 10 to 20 macros. But that basically gives you this thing. And you can run analysis on it and everything. You can run full simulations with it. Okay, now if I want to add Jaroslav's detector, there's one macro, it's the setup EIC detector.c, which basically pulls all the the doors, the hadronic calorimeters, the TPC, well, basically puts everything together into the setup. So just quick and dirty. So the way to add his detector is you edit this file, you add 4 lines at the beginning. Root 6 has to find the include file. So this guy, you have to load the library, preload it. So this is the root 6 way to do that. And then towards the end of the macro, at line 310, before the truth subsystem, which is the last one which is being registered with G4Rico, you basically add these 2 lines, and then you get this. So basically, you can add detectors without doing anything to this thing. You don't have to add any infrastructure. You don't have to modify any common code. You can basically just, with 4 lines, you can slap Jaroslav's thing behind it. And again, the fine print is, you've got the overlap over here. You need to deal with it when you run simulations. And again, it doesn't add the detector, it doesn't magically write the hits out. So that would be, you would have to modify the stepping action in order to get those hits onto our node trees. And also, our world is still filled with air. So again, you need a vacuum system over there. But in general, you can add detectors easily on the macro level to existing setups. So again, there's no common code. People will, you don't step on each other's toes when you do that.
So if you want to add something inside where there is already one detector,
then you would basically go into this thing. We have on top of it, we have some some booleans. So what you would basically do, you would take one of these guys out and put your detector in that place. I mean, yeah, right. Dealing with overlaps, that's kind of your problem then. Yeah, so you have to make sure that it actually fits into that place. But what you basically do, you would just comment out, or modify this thing, just take out something and put your code in there. So we have for every subsystem, we have basically little Jean-form macros which then contain these make a new subsystem. This is the size. These are the parameters, and register with G4 recall. So that's all in separate separate sub macros.
In that macro.
In this directory. I mean, yeah. So this is basically the one which pulls everything, which then calls every single one of them. And since we have 3 different detector setups, this is how we keep our detectors apart.
You may have already answered this, but where do you define all the geometries and things for the detector you want to add? In a separate source file?
So that's an interest of. So basically, again, everybody can do what they want. There is no there's no overarching. Okay, this is how you do the geometry. There are recommendations like, okay, hard coding is how everybody starts, but then you might want to modify to parameters you can set. The way this works is that each detector basically defines its own geometry. And then we take the Jean geometry, export it into GDML, and read it back into TGO. So this is basically how we propagate the geometry into our tracking. But it's not that we start with some giant TGO object, which then has to be modified when you change things in there. So the detector basically, each subsystem knows its own geometry. And we also have the provision that, I mean, you saw all these geometry objects on the node tree. So each detector can basically put information on the node tree, which is important for the reconstruction. So there are reconstruction modules which, hang on. So now when they need information from colorimeters like the tilt angle, that's not necessarily something you find in TGO in the end. But that basically puts this. Okay, my tilt angle is this. Puts it on the node tree, and then with this lookup scheme that you say, I've got detector name underscore, geometry underscore detector name, the clustering or the reconstructor at the end can find these things. So everything goes via the name.
This is done automatically when I put a new detector with new materials. And for the reconstruction, I will need to have the TGO materials.
The TGO is done automatically. I mean, this is being read.
And that is what you use at the level of the reconstruction.
Yeah. Again, it comes with an asterisk, because in the end, what you see is that in the tracking, you spend an enormous amount of time going through this Jean geometry, which is totally not necessary for reconstruction. So, for example, if you have a TPC with many layers in the field cage, the tracking only needs to know how thick is it in the end, and you can get orders of magnitude in reconstruction speed if you have a simplified geometry. But that's a different story.
Okay, so the geometry that you use in reconstruction can be different from the geometry that you use.
In the real world, it actually has to be different, because otherwise you're basically you're spending an enormous amount of time.
Some ancillary programs that do that.
Yeah, for Acts, for example, does this trick. They basically creates a simplified geometry and works with that one. So it uses, I think, whatever the navigator or Giantinos to actually figure out how the density profile for the fits afterwards. But in general, yes. So we take TGO from whatever's in there, and that's what gets fed to the reconstruction.
So I guess if you wanted to add a new subsystem, you have to define all these stepping actions and things?
Yeah. So,
okay.
Yeah, it's basically, again, the stepping action looks...
You do have to write like a source file with all your information on how to handle things.
Yeah, in principle, what you have to implement is a detector class, stepping class, and the subsystem class, which basically bounds everything together.
Okay.
And I agree, the stepping action looks scary, but in the end, it's really cut and paste. So you get help.
By the way, it would be interesting that once a user has created a new detectors in place on another, you can send the code so that it is committed and is available also for the others. I don't know. I don't think that they do have the rights to commit to Git, but
coming up, how we can deal with that. One thing when you replace it, I mean, we've done that. You can imagine, you start with a cylinder, color it, oh yeah, that's a cylinder out of, tungsten or something, yeah. And then you said, okay, actually there's a tower structure and we've got scintillating, so they get more and more complicated. But what we preserved is the idea of a tower. Yeah? So you can have a cylinder, yeah? And you can separate it into eta 5-ins, which you call towers. Just like your real calorimeter, the real setup has also towers, and these towers then get fed to the clustering, and the clustering doesn't know, what the basic detector is. Huh? So there are ways, if you have a new detector and there's an existing reconstruction chain for this type of detector, you can basically funnel your way into the reconstruction chain. Yeah. Okay, help. So yeah, you always get help.
Chris, if I could interrupt, I don't mean to sidetrack you. I've got a number of people in the room here with me at Stony Brook, and a few of us are having some graphics issues. When I'm using my RCF account, I don't get the interactive Géant 4 window to pop. I just lose the prompt. That could be because my account is old and has some crap in it. If you knew something that I should be looking out for, that would be helpful. And then the other comment is I'm also playing around on Singularity under Windows, and in that case, the local setup script doesn't work with $home in the path to your install directory. You have to type it out. So the second was a comment, and the other one was a request for help. If you know of anything that might be odd with popping the display.
With the display, I've had issues. If you look in these vis.mac into the Géant 4 macros, the graphics driver, sometimes OGL seems to work most of the time. OGLIX works, I mean, as the comment said, it works on RCF, but not in the Phoenix counting house on those machines. OGLSX doesn't work on RCF, but so I would suspect, and typically is that there is no display. So it's often the graphics driver, so that.
Right. So is which macro do I look for to change some of those defaults to play around?
I mean, what you should do you use NX?
I am not using NX. No. Do
that. It'll make you a lot more happy, and this all thing will work. I mean, you can take your desktop home and all that. So I would recommend to do that before you start twiddling with graphics drivers, which is a recipe for unhappiness in the end.
Yeah, it's very ugly. Okay, I was just wondering if it was some leftover Phoenix thing that you might say, oh, Tom, unset the blah. But never mind, I don't want to take you off track.
Mm. Yeah, so help, you can always talk to me, that works. Okay, we are working on documentation. So far, what you find over here is just Doxygen from our code base. So we have as Marcus pointed out, we have nightly builds, continuous integration, and from the nightly builds, we make a Doxygen page we create the Doxygen setup every day. So you find it linked over here. The most important one is going to be Mattermost. So that's kind of an open source Slack. It's hosted here at Brookhaven. It works really nicely. We have a public channel. So there's an EIC, forum. So this one, fun4all software support. It's a public channel. RCF accounts can subscribe, so there's no sign up from anybody. Non-BNL accounts, send me a mail and I'll send you an invite. So this can be, again, can be used by non-BNL. And that was quite some doing to get this through here. So we're really proud of that. seems to work nicely. We used it at our workfest a week ago. It was a big success. And okay, the usual last resort, send me a mail or didn't. we always reply.
It will be good to have this in the support structure of the electron ion collider software group. It will of course fill mails of other people too, but to keep an idea and follow also for us what are the problems that they are having. I think it could be more.
I mean, what I would recommend we can make, I would actually make another channel. But the problem with Slack is that you lose your history after a while. So it's in the end they want to sell you something. While this is it's an open source, CERN also uses it. So I would actually recommend to go with MetaMost. What I would like to avoid is to what I would propose basically add channels over here, because you don't want to dilute that. You get like 100 messages a day and 99 of them are not your problem somehow. So to basically focus these helps a bit more.
That can be, but let's start and see if we do have on mails or.
No, I mean, if I hear, I mean, there's going to be questions, and you will need help, everybody. So I'm not. I'll say I don't have any illusions on this one. So final remarks. So that's basically a small selection of the capabilities of fun4all. We used it to simulate and design a new collider detector. It's being built right now. So we basically have everything implemented, from the baby steps where you start with the cylinders to, full-blown calorimeter setups with tilted plates and TPC with electron claws and all that. It has been used to, for EIC detector concepts. So we have a whole bunch of EIC-specific detectors in the system already, which again, everybody on the macro level, you can just import them and use them. There's a there's a large amount of synergy here. So it's a collaboration with an existing experiment. So it means there's going to be long-term support. That's not that, tomorrow we decide to do something else. We are too far ahead with that. So, we're going to have to support this and keep it alive. But that also means there are some warm bodies actually working on it. You can reuse for the analysis. Then you can reuse existing code. So right now we are working on getting acts in tracking into fun4all, because as Phoenix we need it. So we don't have an option not to do that. So that's going to come soon. Sasha Basilevsky just put in some generic clustering algorithm where you basically geometry independent clustering, which is a nice thing everybody can use. Calibrations. An additional benefit, you can read and reconstruct raw data. It's Martin's RC DAC. So that's pretty commonly used in the ERD programs. And here comes your question. How do we actually live to how would we implement these things? As you saw, we already have a GitHub EIC detector organization. So EIC specific detectors, really specific, where can go into their own repository over here. So it's not that you have to ask for permission to get this into Phoenix or so. We can always keep this here. And as you saw, detectors live independent from each other. So we are not going to step on each other's toes. As of yesterday, day before yesterday, there is an EIC CVMFS volume where you basically, where we can build these things. If you have third-party libraries, they would basically could be installed over here. Again, you're not, we are not making any rules, and we're, what can be done. What you guys can do, you can use your own repository, and just link against fun4all and CVMFS. So you don't even have to use this repository. There's a little, okay, this as an organizational thing. To put stuff out on CVMFS, so if we say, okay, fine, everybody can put code somewhere, and we just compile it and put it on CVMFS, there will have to be a little bit of a code review. CERN had an instance or something a couple of weeks ago where somebody mined Bitcoin using their cluster, and that would look really, really bad. So basically, there has to be a bit of sign-off before code gets built commonly and put onto CVMFS. In your own repository, you can do whatever you want. And okay, the distribution uses CVMFS for the libraries. We basically concentrate on a singularity container because there we can actually verify that everything works. If you start supporting whatever 20 different compiler versions and 5 operating systems, it becomes very quickly unmanageable. While over here with Singularity, you basically punt it into the Singularity corner to make sure that everything works on every operating system. And having a Singularity container in CVMFS, you can basically run on the OSG. Yeah. And hey, you made it. It's only 7 minutes after 12.
Thanks a lot. Very impressive. Took a lot of work to put together during a very busy month. And yeah, you were exactly on time. Thank you.
I will set the compiler in CVMFS so that is set and I don't have to worry if I'm using a different compiler and I run in my machine. While on the Singularity, this is not the case, it's already set, but there I will mount all the features which are needed. For instance, CVMFS.
No, we have to see why the Singularity container didn't run for you. I mean, this is basically, there's some, because with that container, it's an RCF operating system image you get there. It has compiler and everything.
Yeah, but I don't see the notes of the.
We have to see why or what's the problem. Again, help is available. We also, what you're going to see is that then.
Also, I will install the root there. That I think I don't know if it is.
It is installed. It should be installed. You should basically.
Since it was pointing to my root in my case. Try different options.
That's basically. The sourcing the setup script should basically set your environment just what you need, and we'll have to find out why it doesn't in your case. And again, C# scripts are poisonous.
But it was going also to bash at the end.
The one thing which is going to come is that we heard Jean 10.6 is on the horizon. It doesn't compile with RCSL and doesn't compile with the SL7 stock compiler, so 4.8 doesn't compile Jean 10.6, and we have a version of everything compiled with GCC 8.3. So again, source another setup script to get the 8.3 setup, which is then also needed by acts.
Yeah, and that is something that you can manage at the CVMF level.
Yeah, exactly. You source another setup script.
Yes.
And,
The compiler is distributed
under
the Singularity. So we can help. We can work together. The logic probably
Yeah, but it can go also for if I want to use not the Singularity but my own installation. If you have a compiler which is mandatory, you better set it at the level of the sourcing of the script that we are doing.
Yeah.
But there are distribution of HCZ where you can find it.
Yeah, but inside Singularity, it should actually.
In the Singularity,
it should
I
do
don't
that,
care.
yeah.
Let's say that I do agree.
Everybody hungry?
Okay, we have a generously timed lunch break because there's no food on site, except for those who have signed up for pizza. If you're not a fan of pizza and don't have a car, I hope you pair it up with somebody who does have a car. Is anybody in a tight spot for a ride to lunch? Everybody's fixed. The pizza will arrive about 12:30, sorry. In the lobby, feel free to make a lunch of cookies and crudités if you prefer to do that. Keep it simple. And so we'll resume at 2 o'clock with the G4E tutorial. Thanks, everybody.
I can run a few more tutorials if you guys want to.
February 6th.
Nice job, guys. So far, so good. Yeah. So here's the list of our tutorials, by the way.
It's almost
Yeah. No. I was about to say, I don't think there's a bathroom.
So, projector off.
That's the
And then we might just mute the microphones as well. You can bring the lights up all the way. But yeah, I think you're pretty